So the theme I have selected for this presentation is energy metabolism. And the reason for doing so is that energy metabolism is one of the most fundamental features of life. Without energy, life can't occur. And it's controlled on a plethora of different levels in a multitude of organs in our organism. So the model we are looking at is the liver and the pancreas islet. And the reason is because those are most central in energy metabolism control, and they're also entangled in an almost symbiotic way with each other. And knowing that they are so important and that they're so closely entangled, it is kind of puzzling why humans use so much efforts to mess up this beautiful interaction between the two organs by all kind of different factors, mostly unhealthy lifestyle. And so what that leads to very frequently is to a transformation of a healthy liver into a fatty liver. And that then feeds back in an almost in a triangle of organs and diseases, including NAFLD, obesity, and to type 2 diabetes, to a mechanism where you have increased gluconeogenesis, you have increased glucose uptake, you have, as a consequence, hyperglycemia, you have an increase of fatty acids, and you have an increase in inflammatory cytokines, and that all starts slowly to circle out of control. So it is really a huge problem in the human population. The prevalence of NAFLD is around 30%, and it's 3 times higher in patients that have type 2 diabetes. It's estimated that in the US alone there are 18.2 million people that are living with type 2 diabetes and NAFLD, and 4.6% of those have also NASH, which is the next phase of the disease development. 20-year cost of NAFLD is around $55 billion. So these are huge numbers, and they justify that we need to look into models that address this disease or disease group for testing interventions. The models we are looking at, obviously in the frame of this conference, are organoids and organ-on-chips. So what I will talk about is, first of all, a background placing this disease group in the large field of organoids and organ-on-chip models. Then I will tell you how we have been and are developing pluripotent stem cell derived liver and islet organoids for our modeling. Then I will talk about our development of a novel organ-on-chip platform to house those organoids. And then I will show you data on using this new platform together with our PSC-derived islets and livers to model first the metabolic interaction between those two entities, and then to model disease. So just to give you an overview on the field, and maybe it's a bit weird if you do that at the last sessions, you should rather do it on the first session, but I want to put those data in the context of the work we're doing. So we have been recently doing a meta-analysis of all the organoid and organ-on-chip field. And the first thing you see is that there is an amazing increase in the literature, which is no surprising. It's a hugely interesting field. We have a 50% increase each year in the academic literature in the field compared to, for example, 6% in cancer. So it's hugely at catching attention. Now, what we have done in the frame of this meta-analysis, and I will soon show you why we did that, a categorization of all the organoid and organ-on-chip models that are around, and we have placed them then in subcategories and further subcategories. In addition, we have put a trend line on it to see what kind of models are trending in the last 2 years. Where is the tension in the field? Now, this is a graph that is, you will not be able to read it from any distance, so we choose to get a better graphic representation of this model, which we call Celtic circles. And there you can see which of the fields and which of the subfields are trending and which are more stable over time. And if you look at the field that we work with, which is hepatic and pancreatic models, we see it's maybe not particularly trending. But the reason for that is that it always has been trending, so we have a stable interest over time in the field. And the same holds true for organ-on-chip. You see up there, it's a large field, it's a large subfield in the area. It's not particularly trending, but it has been stable over the time throughout the period when people have been working on microphysiological systems. Now, having done this analysis, it's over 10,000 articles that we read in by machine reading and then categorize. We can do all kind of analysis. One is we can look at the cell source, and here it's segregated organ-on-chip versus organoid, which is one of the questions we can ask to the database. But also we can look then into disease models that are addressed in different platforms. And we will see that here, for example, obesity and fatty liver, but also diabetes are certainly areas, disease areas that are worked on quite significantly in the field. So we can then, and again you will not be able to see all the details, we can then segregate the disease groups into which organs have been addressed and with which platform they have been addressed. For example, has organoid technology been used or has organ-on-chip technology been used? This article is now under revision and will probably come out in a month or so, and then you can look at the database yourself and you can use it for harvesting and interrogating with your own questions. One of the things, and that's why I show all that we also can do is we can show what kind of different organoid or organometals have been combined in different platforms. And this is a circle where we show which organ representations have been combined in dual or triple or multiple chips. And you see here is the hepatic pancreatic biliary model. You see that this model is mostly combined with lung, heart, gastrointestinal, but so far not so much really with each other. So this gives a rationale for us to investigate some effort in building up a dual model combining islets with liver. And this is then the workflow that I want to present you from the work we have been doing. So first of all, we establish a platform for deriving functional liver and islet organoids from PSCs. We use both ESCs and iPSCs. We then test those and benchmark them to adult tissue. We then have developed and are developing a platform to house those organoids, and then finally we co-culture them and interrogate them. The way we differentiate the hepatic lineages is rather standard. So we derive hepatocytes, liver sinusoidal endothelial cells, stellate cells, cholangiocytes from PSCs. We haven't yet been working on Kupffer cells. And then we subsegregate the hepatocytes into zone 1 and zone 3 hepatocytes, where I think we are quite advanced in the field. We do that as one would do commonly. We would try to follow the developmental trajectory that leads to those lineages, and by doing so we get quite nice liver organoids that we then benchmark to the adult tissue derived from corpses. Now you see in that graph that, similar to many other efforts to get liver organoids, those are not quite that mature as adult liver organoids. Nevertheless, they're quite good in albumin and urea production, and they're also quite good in cytochrome P450 activity, although, as I already mentioned, not as good as tissue directly derived from human corpses. In addition, we do a number of functional tests, for example, activity of transporter and glycogen storage, to which I will not go into any detail. We do a number of further downstream tests, which I think are rather unique. One is a test where a colleague of mine, Stephen Wilson, in Oslo, has developed a platform that is called electromembrane extraction platform, whereby you put either media or directly organoids into a multi-well tube that is separated by a lipid membrane, and then you will have a canal underneath the lipid membrane that is compatible with LCMS, and so the metabolites that are passing the membrane through an electric currents and get into the chamber that is connected to the mass spec will then allow directly to measure metabolites as they occur and accumulate while the organoids are exposed to a drug challenge. And here we have challenged them with heroin, which is metabolized to morphine, and then you will see that we do have a quite good phase 1 metabolism in the organoids that we have grown and that we can directly measure by MS. The other technique that we have been working on developing with Molly Stevens in a close collaboration is to look into these organoids by Raman confocal imaging that should give you a possibility for chemometric measurement of what's going on in these organoids. And this gives an additional tool to other analytical technologies like single-cell RNA-seq or proteomics or metabolomics. What we have been using it for is two things. One, we have been using it for benchmarking the organoids within a batch. So how is the variability of the organoids versus each other in a certain protocol? And then we have been using it to benchmark the organoids to primary or to spheroids derived from primary cells. What we also have been then doing is to see whether we can follow drug metabolism in these organoids by Raman confocal imaging, and amazingly enough, this works. It does not work for all drugs. You need to have some drugs that are particularly Raman active, but with neratinib, we were able to see the accumulation of the metabolite in vesicles within cells in the 3D organoids, and also we could see that it accumulates in some canal-like structures between the hepatocytes in the organoids. So that's quite an amazing technology. It's unfortunately not yet a live technology, so this is on fixed tissue, and we're now working towards getting that into live imaging, which is a considerable challenge given the sensitivity of the technology. But we'll see. Stay tuned. So as a next step then, to achieve further metabolic maturity, we have been working towards getting those liver organoids zonated, and I have to say that all the liver work is by Alexandra with the help of Justina and several in the lab. Alexandra is really an amazing scientist. You come in the morning, she's working. You come in the evening, she's still working, and it bears fruit. So the thing she has been working out is how can we get these liver organoids zonated. You know that there is a quite significant difference between the position where liver hepatocytes are as to the portal triad or the central vein. And so what she has achieved is that she has created liver organoids that are either zone 1 or zone 3 and have particular metabolic activity that now matches the adult derived in spheroid-grown hepatocytes. What I'm particularly happy about is that you see that they don't only have differences in their metabolic activity, but they also have differences in the way where beta-catenin is positioned. You want to have beta-catenin positioned in the nuclei in zone 3, and you want to have it positioned in the membranes in zone 1, and that's exactly what we see. So I will then briefly spend a few minutes on the other lineages that we have been producing. We have been producing liver sinusoidal endothelial cells. Those seem to approach metabolic activity, so they produce factor 8. We also see that they have some features which we're not entirely sure whether that is fenestration. It's a bit too big for fenestration. What you see there is a tomocoupe holographic imaging, which is a new technique that allows you label-free detection of subcellular structures. We confirmed, though, the presence or the likely presence of this fenestration with electron microscopy, and that's mostly the work of Mikkel in the lab, a very talented young researcher that has focused the last 3 years to get those liver sinusoidal endothelial cells to reach a certain level of maturity. And then we also have been working on the stellate cells, which are the parasites, very important to support the liver sinusoidal endothelial cells. And I just want to show you this picture that should give you an indication that rarely those cell lines are very happy alone. So what we have discovered is that if we grow stellate cells or liver sinusoidal endothelial cells over 2 weeks, they very quickly deteriorate. They deteriorate even worse if they're derived from corpse material, but also if they're stem cell derived. If we co-cultivate them, then we see with some parameters that they're now much happier. And for example, here I show you the vitamin A storage, which is an important parameter of stellate cells, which is dramatically improved if you co-cultivate these cells. It could be very important to have some of those cells being co-cultivated. Now I want to very quickly jump into islet cells. This is the work of my collaborator Hanne Scholz and Cheng Wang, a very talented Chinese PhD student, and he has pushed PSC-derived islets to a stage where they not only show a response to pyruvate, but they also show a 2-peak response to a glucose challenge, which is really good. And also, if you compare the oxygen consumption of adult islets versus PSC-derived islets, we seem to have a rather good match. I wouldn't say that they entirely mature that, but they're really approaching maturity. And with that, both islets and liver organoids can be or reach a degree where they can be used for disease modeling. Now I come to the next part of my talk, and that is then the platform development. So you have heard a lot about platforms, microfluidic platforms that are being around and used and developed. They all have their pluses and minuses, so there's no fit-for-all solution. So you have, if I just categorize them very briefly, 3 different systems. One is pump-driven directional, the other is pump-driven directional where the pump is on the chip, The first was the pump outside of the chip. And then you have a rather simple but very efficient way whereby simply 2D tilting, you get a flow back and forth in the chip. Now the last thing is very scalable. The first two are not very scalable, although it is attempted. So we were questioning, is there any way to get a directional flow without all this pumps and tubing? We also looked into material, and I don't want to dwell onto that too much, but we have chosen to use PMMA for our chip development. And the main goal was to do something really simple and with that scalable and robust. The way we have approached that is to turn 2D tilting to 3D tilting. And that seems to be a very, very simple principle, but strangely enough, nobody has followed it up. So Matthias Busek, who has first worked with tissues and has luckily joined our center, has developed a platform that is based on 3D tilting, and that gives a directional flow without the need of any pumps or any tubing. And he's now developing 3 different iterations of that. One is single loop, the other is loop-in-loop, which allows 2 circuits, and double loop. And I will present you some data from that very soon. We also work on upscaling and manufacturing. We're not yet quite there, but I hope that we will be there in a few months. And I want to give you just a very quick flash what this platform can. So it does give you directional flow. The shear stress in the flow, the wall shear stress, can be regulated by the tilt and the speed. That gives us oriented epithelialization, which is very important for a multitude of processes in the canals. And the epithelial cells line the chamber in which the organoids will be placed. This allows us to get vascularization into the chamber where we house the organoids. And in addition, the system is compatible with introducing immune cells, which then allows us to develop an immune compatible and immune competent chip without tubing. One of the experiments that is currently ongoing is to see whether we will get penetration of monocytes through the wall of through the endothelialized wall into liver organoids that are damaged as a disease model. I will not dwell on that because we're short of time. As I already indicated, we are also looking into ways how this production of this chip can be upscaled and with that made accessible for the community, and that's a work that Matthias is doing together with Setfan. There were posters for all that. So, coming to the combination of 2 organoids in this chip platform, and so we have first adapted one of our chips, the double loop chip, to house both islets and liver, and we need a bit different chambers to house them because the islets have a very high oxygen consumption, so they need some different configuration. What we see though is in this configuration the islets seem to be rather happy, and also the liver organoids are rather happy. Now if we go into more detail and see how they react to functional stimuli, we will see that if they are combined, and if they're combined for 14 days, they will have improved insulin secretion upon glucose stimulation as compared to a static or monoculture. That's very good because now we have a system where we can maintain these cells happy for at least 2 weeks. We also see that when we combine them in co-culture, and I find that very important, that we have a reduced cytokine protection, inflammatory cytokine protection. So they seem to be overall quite a bit more happy if they are co-cultivated in the dual chip. But what's most interesting is that the islets that are co-cultivated in this chip with liver produce much less MCP1. MCP1 is one of the catastrophic cytokines for islets. On the liver side, we see that albumin is maintained, and we also see that urea production is increased in the culture, in the co-culture compared to single culture. We then also see, and that's also quite important, that we see an improved response to drug metabolism in the liver organoids. So overall, it seems that we can phenocopy the symbiotic interaction between islets and liver in this chip format. And so we can start to look at disease models, and the experiment that we have done so far is to induce NAFLD in healthy liver organoids. We then check with different markers. This here would be SERPP1, which you see is an indicator for these organoids really being fatty liver organoids. But also we looked into oxysterols, and we see a very significant increase, indicating that we have induced a NAFLD phenotype. And then we have massive lipid droplet accumulation, as you would expect. We also looked then into glucose oxidation, which is an indicator for insulin resistance, and we do see evidence that we start to get insulin resistance in the hepatic organoids upon inducing NAFLD. And that brings us then towards the end, that we combine the diseased liver with the healthy islet organoids, and we see that they again start to crosstalk. The first thing that we find is that over time, the islets that are combined with the diseased liver organoids start to deteriorate very quickly. So this healthy interaction that you would see with non-disease-induced livers is somehow interrupted. What we then also see that the glucose-stimulated insulin secretion is deteriorating in the islets. We see that also the liver obviously is getting poorer over time, and we see that glucose is increased and insulin consumption is reduced. If we then look again at the cytokines, we see that the diseased liver induce a number of inflammatory cytokines in the islet, but in particular, I want to point out again MCP1, the very aggressive cytokine that attracts monocytes, which is now increased on the islet side of the dual chip. So that gives us a very beautiful model system, I think, to combine liver and islets and to model disease. And the next steps, and here come to the summary and outlook, is then that we will use this model in two ways. One, we will start to look into drug interrogation on the chip, and the second is that we will look whether we can modulate immune interactions and the response of the immune interactions to drug interventions. And with that, I will thank you, and I want to thank all the people that have been involved in our work and that have funded our work. Particularly, I will highlight 4 people. They're all here. There have been many more working on that, but maybe you have seen them and their post, and that's Alexandra here to the left. That's Matthias, the chip developer. That's Ingrid and Koyoko, who all have been contributing very significantly to our work. Thank you very much.
Thank you so much, Stefan. So we have a short time, so only a quick question.
Thank you for your beautiful talk. You mentioned that you saw that the LSECs were helping to maintain a better phenotype for hepatic stellate cells. Did you see that it was also impacting the phenotype of LSECs, having the other cells nearby?
I didn't understand.
You mentioned that the LSECs in co-culture with the hepatic stellate cells had a positive impact on the hepatic stellate cells. But did you check the LSEC phenotype also? Was the co-culture better for them?
Which phenotype?
Of the LSEC, the liver sinusoidal endothelial cells?
Oh yeah, sorry. Yeah, no, we haven't. No, we haven't so far. But that's a very good question. Yeah, yeah.
Thank you.
Thank you so much, Stefan, again.